Hi and welcome back. This is Pankaj here. In the last video on probability, we have understood the different ways or different approaches towards probability, and I also mentioned that we're going to be learning Ematic Approach towards probability. We've also defined the different events that we have under probability, like the mutually exclusive, the elementary events, and the compound events and exhaustive events, mutually exclusive and exhaustive, and so on and so forth. We have also defined something known as a sure event, right? A sure event or a certain event, otherwise called as a certain event, and an impossible event. Okay, so these are the different types of events that I have already mentioned in the previous video. Now we're going to look at what is the axiomatic approach towards a probability. Let me pull up the definition for axiomatic approach. That's the definition for axiomatic approach on probability. What does it state? It states that for any sample space, okay, for any sample space, if the individual outcomes are omega 1 and omega 2 and so on till omega n, that's the elements belonging to the sample space, okay, then the probability of any particular element is always going to be a 0 or equal to 1. Okay, and it also states that probability of individual items or individual elements, you add them up and it will always give you 1. Okay, and 1 is actually the probability of the sample space. We will understand this. Okay, and for any event defined on this particular sample space, the probability of the event is given to you as the probability of the elements belonging to that particular set itself. Okay, let's say, for example, I'm taking up a die and throwing the die. So I already know the sample space for it. The number of options is going to be a 1, a 2, and a 3, and a 4, 5, and 6. Correct? Now, let me explain to you what is an impossible event. We already do know what's an impossible event, but I'm going to define an impossible event for you. Let's say an event A is defined to you as getting a 7. Well, this is an impossible event, which means the set itself is a null set, which means the number of elements belonging to it is a 0. Okay, so what is the probability of this particular event? The probability of this particular event can be defined as number of elements belonging to A divided by number of elements belonging to the sample space, which is going to be 0 divided by 6, and that's a 0. So the least probability that can be assigned to any event will be a 0. Okay, I cannot have a negative probability. That doesn't make sense. Okay, and you will not have an event where a negative probability will be assigned. Okay, that's not possible either. Now let me look at a sure event. A sure event. Let's say I'm defining a particular event B as getting a number less than 7. When I define the event as getting a number less than 7, the possible options are going to be 1, 2, 3, 4, and a 5, and a 6, which is already been mentioned here. So the number of elements belonging to B is going to be a 6. So what's the probability of B? Probability of B can be defined as n of B divided by n of S, which is going to be a 6 by 6, which is a 1. And that's the maximum probability that I can assign to any event, okay, which is a 1. Any other probability will be in between 0 and 1, because the number of elements of that particular event is either going to be a 0 or a maximum of 6. Okay, so anything else which is from 0 to 6 divided by 6 is going to be a proper number or a proper fraction. It's going to be a proper fraction, and we already know that a proper fraction is always less than 1. Getting me? So that's my first condition explained to you, that the probability of any event is always going to be between 0 and 1, which is true. And you can, in this scenario itself, we can take up probability of these individual items. Every element in this particular sample space has equal chances of appearing, right? When I throw the die is made in such a way that all the 6 numbers on the die has equal chances of appearing on the table, isn't it? That is when they have equal chances of appearing. So probability of all of them will be equal to 1/6. Now when I sum up all the probabilities of individual items, which is probability of 1 plus probability of 2 plus probability of 3 plus probability of 4 plus probability of 5 plus probability of 6. When I add them up, I get a 1/6 plus 1/6 plus 1/6 plus 1/6 again plus 1/6 plus 1/6, which is nothing but 6/6, which is a 1. Correct? So I've just gone ahead and proved that assigning probability using this method satisfies the first condition, which is it's going to be a greater than 0 number and less than a 1 number. And I've also just gone ahead and proved to you that the events, if the individual elementary events are equally likely to appear, then the probability of individual items summed up will give the probability of the sample space, which is actually equal to 1. Now I'm going to now define a event as getting an even number. Then the elements belonging to that is 2, 4, and 6. Now the probability of A is simply n of A divided by n of S, which is going to be 3/6, which is a 1/2. Okay, now that is nothing but equal to probability of 2 plus probability of 3, probability of 4 plus probability of 6, which is going to be probability of 2 is nothing but 1/6 plus 1/6 plus 1/6, which is again 3/6, and that's a 1/2. Same probability. So what is now the function or the way to assign a probability to a particular event from the sample space? It is nothing but number of elements belonging to that particular sample space or belonging to that particular event, okay, divided by total possible options, which is number of elements of the sample space. Okay, it is the same approach, but we learn it in the axiomatic way. All right, any function which can actually do this will be called as a probability function. A function which can assign probabilities to the event is the probability function. Okay, so in this case we have understood that m by n, that's the probability function, m by n, where m is the number of possible elements belonging to the event A and n is the number of elements belonging to the sample space. Okay, all right, great. Now what we're going to do is we're going to look at a few examples from the textbook. It is not very different from what we already know. It's the same thing, but we again learn that in a different way altogether. Okay, so let's take up an example. The questions which I'm going to be doing right now, you might feel that the same thing that we have done already, and yes, it is the same thing. Okay, it's only that the concept of applying probability changes a bit, not to a very great extent, a little bit. Okay, let's say, what's the probability of getting ahead? Getting ahead. Well, it's very easy. The sample space is going to be head or a tail, because those are the possible options when I toss the coin. The random experiment is tossing the coin. So only two options, either head or a tail. And the event is being defined to me as getting ahead, which is H alone. Correct? So what is the probability of A? Probability of A is defined as n of A divided by n of S, which is nothing but 1/2. Okay. Now what happens when I toss the coin twice? When I toss the coin twice, I have the total possible options, which is head head, head tail, tail tail, tail head, isn't it? Any other possibility? I don't think so. That's it, right? So now I'm going to be defining an event A, which is getting at least one tail. Getting at least one tail, which means the elements belonging to this is going to be HT TT, TH. At least one would mean one or more than one, correct? So it is one or more than one. So what is the number of probability of A now? The probability of A is simply going to be number of elements of A divided by number of elements of S, which is simply 3/8. Okay, I can either calculate the probability of A in this fashion, or I can find the probability of HT from the sample space. Probability of HT from the sample space is 1/4. Oh, N of S is 4, I'm sorry. N of S is a 4. So I'll have to change that. This is a 3/4. Correct? Now, what is the probability of TT? Is going to be again a 1/4. And probability of TH is going to be a 1/4. You see, that's 3/4. Okay. Now, what if I'm tossing the coin 3 times? Then the sample space is going to change, isn't it? H, 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 tail, tail, H, tail, H, 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 tail. And I think that's it. Okay, now with tail, 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 head, head, tail, tail, head, and tail, head, tail. Any other options? I think that's it, right? So now I'm going to be defining another event. Let's say A. I'm defining it as getting to head. Okay, I'm defining the event as getting 2 heads. So the elements belonging to this is going to be the options where only 2 heads are available, which is this, this, and this. Okay, so that's going to be a H, T, H, 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 T, and T, H, H. So the probability of the event A can be defined as number of elements belonging to A divided by number of elements belonging to the sample space. In this case, it's going to be what? 3/8. Okay, so that's the basic idea of probability. Nothing difficult. It's very, very easy. Furthermore, we will be looking at difficult questions. These are very easy questions. I'm doing them so that you can get the idea behind probability. Okay. Now what I'm going to do is I'm going to pick up another question. Let's say I'm throwing the die. The random experiment is throwing the die twice, and with this I'm going to be finding the probability of an even number as the sum, which means I'm going to throw the die and then check what are the outcomes of that particular trial. And in that trial, if I get let's say 1 and a 3, which sums up to be a even number, which is actually 4. So I'm trying to find out the probability of such things happening. Okay, and I'm also going to be finding the sum as prime number, and also a total of at least 10. Now when I'm throwing the die twice, I already know the sample space. It's going to be a 1 1 1 2 1 3. Yeah, it goes on till 6 6, isn't it? So let me write that for you. The sample space is going to be what? 1 1 1 2 goes on till 1 6. Then I'll have a 2 1 2 2 goes on till 2 6, and then I'll have 3 1 3 2 goes on till 3 6, and here it goes on till 6 1 6 2, and this goes on till 6 6. Correct? Now in this, let's look at okay, what is the number of elements of the sample space? Number of elements of the sample space, how much is that going to be? Well, this I can again do in probability way, permutation way. I'm filling up 2 boxes. The number of ways of filling up this box, I can have any of the 6 numbers, isn't it? 1 to 6. So 6 ways of filling this up. And this way is a number of ways of filling the second box is again going to be 6 ways. So total number of ways of doing this is 36 ways. This is the fundamental principle of multiplication. So basically I'll have 36 outcomes. Okay. Now in this, I'm now looking at the sum to be a even number. Okay. So probability of, or the number of elements belonging to this. Let's see what that is. Okay, now if the sum has to be an even number, there are two options. One, both the numbers appearing on the die should be even. The first time throw should give me an even number. The second time throw also should give me an even number. When that happens, I for sure know that the sum is going to be an even number, so both should be even. Or both can be odd. You add any two odd numbers, you will always get an even number. 3 plus 1 is 4, 5 plus 7 is going to be a 12, 13 plus 3 is going to be a 16, right? So you take up any odd number, add them up, you will always get an even number. So the two options is both are going to be even or both are going to be odd. Okay, now which means I have to leave out all the options where one of them is a odd and one of them is a even. This particular option I cannot consider. Okay, so I can write it down. So it's going to be a 1 comma 1 is a odd number, so I can pair that with the odd number only. 1 comma 3, 1 comma 5, and that's it. 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, nothing else. And then 2 comma 2, 2 comma 4, and 2 comma 6. Now 3 comma 1, 3 comma 3, and I think 3 comma 5, right? I didn't write a 1 comma 1 here. Okay, then 4 comma 2, 4 comma 4, and then a 4 comma 6, and then a 5 comma 1, 5 comma 3, and then a 5 comma 5, right? And at last I have a 6 comma 2, 6 comma 4, and a 6 comma 6. You understanding? Okay, so how many possible options? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 18 possible options. This I can also do it in permutation and combination way. I'm going to consider two situations where I'm trying to find out how many evens are going to be there. So first time I'm going to fill the boxes only with even numbers. So 3 even numbers here, 2, 4, or a 6 to be filled up here. Again 2, 4, or a 6 here. Correct? Now what if I have to fill both of them to be odd? Both of them are odd numbers. Then 3 options here, 1, 3, or a 5, and again 3 options here, 1, 3, or a 5. So how much is 3 into 3? It's going to give me 9. Again 3 into 3, which is 9. So the total, plus them up, add them up, I'm going to get 18. You getting me? This is another way of doing the same question, right? So here too I got 18. 1, 2, 3, 4, 5. 1, 2, 3, 15 plus 3, 18. Getting me? So now let's go ahead and find out the probability of A. The probability of A is going to be equal to n of A divided by n of S, which is nothing but 18 over 36, right? That's going to be a 1 over 2. Let's look at one more example in this particular video, and then we will move on. For this example, what I'm going to do is to pick up playing cards. Okay, so if you can see here, I have one full deck of cards, and these are the 4 variants of the cards that I can have. Okay, so the cards, every variant is going to have A to K, right? So this is your A1, that which is a 1 actually. It's a 2, this is a 3, 4, 5, 6, 7, 8, 9, 10, and this will be the 11, which is J or a Jack, and this is the Queen, which is the 12, and K, which has the value of 13. Okay, let's look at this. The spade is going to be this, which looks like a leaf. Okay, and the heart, the diamond, and the clubs. Okay, so the club and the spade are black cards. Look at that. The club and the spade, these are the blacks, right? And this row and this row, they're all blacks, and this row and this row are going to be all reds. And this is called as a ace card. Okay, So let's go down here. So now this is going to be a spade. This is a spade, and this is a club, which is black. This is a heart. Well, it's visible, and then this is a diamond. Okay, so altogether I have 13 cards in each. So this will have 13, this will have 13, this will have 13 cards, and this will have 13 cards. So altogether I'm going to have 13 into 4, which is 52 playing cards, except for the jokers. We don't consider the joker. Okay, now if you can see here, A is number 1, which is otherwise called as the ace card. ACE, ace card. Okay, and these are my face cards. Okay, these are called as the face cards, and all these are my numbered cards. They have a number on it. Getting me? So this is the numbered cards. Okay, so this is a typical playing set of cards, or a deck of cards, it's otherwise called as. Okay, so let's look at a question from here. Let's look at a question based on this. Okay, now let's say I'm choosing a card from a deck of cards, and I'm finding out what is the probability of me getting a ace card. Okay, now when I'm thinking of the sample space for this, I need to understand that I can pick any one of these cards, which means all of this is a sample space. This is actually the sample space. So what are the total number of elements belonging to the sample space? It's the number of cards I have in the particular deck, which is 52. So the probability is number of aces divided by number of cards, isn't it? And the number of cards is going to be 52. And how many aces do I have? Which is ones. I have 1, 2, 3, 4 ones. So the probability of me getting an ace out of 52 cards is going to be a 4 over 2. 4 over 52. Okay. Now what about me getting a face card? What's the probability of me getting a face card? That's going to be number of face cards divided by number of cards in the deck. So the denominator I already know, it's going to be a 52. But what about the numerator? How many face cards are there in the deck of cards? So there is 1, 2, 3, 1, 2, 3, 4. I'm going to use another ink. Let's say, okay. So 1, 2, 3, 4, and then 3 in this. So 12. So 12 face cards divided by 52. Okay, so that is the probability of me getting a face card out of a deck of cards. What about me getting numbered cards? Probability of numbered cards. Okay, for that I need to find out how many numbered cards are there. So this has like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 fours are 36. So 36 out of 52. Got it. And what's the probability of me getting a black card? Probability of a black card. So I need to identify how many black cards are going to be there. So I do know that spade and clubs are the type which has black. So which means 13 plus 13, which is 26. 26 divided by 52. So that's the probability. Correct? So that's it with this video. I'm going to be doing more videos on probability, picking up more examples, and we're going to be also learning permutation and combination along with probability. Okay, simultaneously I'm going to be explaining to you permutation, combination, and probability. With that being said, I would like to end the particular video. Thank you very much for watching it, and again, subscribe to the video and share the videos. Thank you.